Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shukri Nazmi bin Muhammad Nazim. Today my group will discuss about the IEEE 1159, which is recommended practice for monitoring electric power quality. First of all, what is IEEE 1159? IEEE 1159 is a recommended guideline that provides the user with a consistent set of terms, definition and practice for describing power quality phenomena. This includes the appropriate technique for power quality analysis, for example, the monitoring location, the appropriate studies, and appropriate interpretation of the power quality phenomena. The term power quality refers to the wide variety of electromagnetic phenomena that characterize the voltage and current at a given time and a given location of the power system. The increasing application of electronic equipment that can cause electromagnetic disturbance or that can be sensitive to this phenomena has heightened the interest in power quality in recent years. These are the type of the power quality disturbance that occur during a period of times with its amplitude. The first power quality phenomena is the transience, or in other terms, the surge. Transience consists of two types, which is the impulsive and oscillation. The impulsive is a sudden non-power frequency change from nominal condition of voltage and current. It is unidirectly in polarity. It is normally characterized by peak value, rise and decay, or duration time. Most common cause of the impulsive transition is the lightning. The duration of the transient the impulsive transient is from nanoseconds to milliseconds. The second one is the oscillation transient. It is a sudden non-power frequency change in steady state of voltage and current. It includes both positive and negative polarity. The instantaneous value change polarity rapidly and decaying within fundamental and frequency cycle. It can be measured without fundamental frequency included. The duration of the oscillation transient is 3 microseconds to 5 milliseconds with the amplitude of 0 to 8 per unit. The next phenomena is the short duration RMS variation. Short duration RMS variation is caused by the fault condition in a power system. There are three types of short RMS variation. The first one is the interruption. The interruption is the supply voltage or load current decrease to less than 0.1 per unit for a duration of less than 1 second, for less than 1 minute. The next type is the voltage sag. Voltage sag is a decrease in voltage which is between 0.1 to 0.9 per unit for a duration of 0.5 cycles to 1 minute. Voltage swell, on the other hand, is the increase of the voltage which is above 1.1 per unit for the duration of 0.5 cycles to 1 minute. It is typically between 1.1 per unit to 1.2 per unit. The next phenomena is the long duration RMS variation. For short duration RMS variation is the duration for period the period of the duration is below 1 minute. The long duration RMS variation happens for above 1 minute. It can be characterized into two parts, which is the under voltage and the over voltage. The under voltage is a decrease in RMS voltage which is less than 0.9 per unit for a duration of 1 minute, above 1 minute. It is commonly caused because of the load switching or capacitor bank switch off. The over voltage, on the other hand, is the RMS increase in AC voltage which is greater than 1.1 per unit for a duration of more than 1 minute. It also caused because of the load switching or the capacitor bank switch on. The next phenomena is the voltage imbalance. Voltage imbalance is the ratio of magnitude is of negative voltage sequence to the positive voltage sequence, with the normally expressed as percentage. Typically, in three-phase system, the voltage imbalance is below 5%. The current imbalance are higher, especially when one-phase load are presented. The next phenomena is the waveform distortion. Waveform distortion is the steady-state deviation from ideal power frequency. There are 5 types of waveform distortion, which is DC offset, that with amplitude of 0 to 0.1%, harmonics with 0 to 20%, interharmonics 0 to 2%, notching, and noise with 0 to 1% of amplitude. The next one is the voltage fluctuation. Voltage fluctuation is a systematic variation of voltage envelope or a series of random voltage changes between 0.1 to 7% in amplitude. Such variation can be seen by human by changes in lamp illumination intensity. The last one of the power quality phenomena is the frequency variation. Frequency variation is the deviation of power system frequency from its nominal value. A steady-state power frequency is directly related to rotational speed of a generator of a system. The frequency depends on the balance between the load characteristic and the capacity of available generation. Outside the accepted frequency limit can cause the fault on board power transmission system. Thank you.
Alright, I will continue with IEEE 1159 standards, which is the monitoring of power quality. So this is the objective for the monitoring for the quality. Power quality monitoring is necessary to characterize electromagnetic phenomena at a particular location in an electric power circuit. In some cases, the objective of the monitoring is to diagnose incompatibilities between the electric power source and the load. In others, is to evaluate the electrical environment at a particular location to refine modeling techniques or to develop power quality baseline. In still others, monitoring is used to predict future performance of load equipment or power quality mitigation device. In an event, the most important task in any monitoring project is to clearly define the objective of monitoring. The objective of monitoring for a particular project determines the choice of monitoring equipment, the method of collecting data, the triggering threshold needed, the data analysis technique to employ, and the overall level of effort required of the project. The objective can be as simple as verifying steady-state voltage regulation at the service entrance or as complex as analyzing the harmonic current flow within the distribution network. The procedure for defining monitoring objective differ by the type of study. For example, when the not-state monitoring is used to solve shutdown. With sensitive equipment, the objective should be captured out of tolerance event of certain types. Evaluate or predictive monitoring should require collection of several voltage and current parameters in order to characterize the existing level of power quality. So, why we need monitoring power quality? Why we must monitor the power quality? So, the most important reason is the economic reason. There are several important reasons to monitor power quality. The primary reason defining all the other is economic. Particularly, its critical process loads are being adversely affected by electromagnetic phenomena. Effect on equipment and process operation can include misoperation, damage, process disruption, and other such anomalies. Such disruptions are costly since a profit-based operation is interrupted unexpectedly and should be restored to continue production. In addition, equipment damage and subsequent repair cost both money and time. So this had the effect to the economic for the certain operation. They will cost the money and time. In addition to resolving equipment disruption, database equipment tolerance and sensitivity can be developed from monitored data. Such a database can provide a basis for developing equipment compatibility specification and guideline for future equipment enhancement. In addition, a database for the causes for the recorded disturbances can be used to make system improvements. Finally, equipment compatibility problems can create safety hazards resulting from equipment misoperation or failure. For equipment tolerance and effects of disturbance on equipment. The tolerance of equipment needs to be considered in power quality monitoring. For example, a specific ASD can be sensitive to an over voltage or under voltage condition, but there can also be significant variation to the same phenomena among ASDs built by other manufacturers. So power quality monitoring should attempt to characterize individual process equipment by matching monitoring result with reported equipment problem. This characterization of individual load shows which equipment needs protection and what level of protection is required. Next, the equipment types. Although there can be a wide variety in the response of specific equipment types manufactured by different companies, there can be some similarity in the response of certain type of equipment to specific disturbance parameter. In case it's useful to consider certain specific equipment types or grouping in terms of their immunity to power quality disturbance.
Okay, the measurement instruments is an instrument used to monitor electromagnetic phenomenon. Can range from a simple analog voltmeter to a sophisticated multiple-site permanent install power quality monitoring system. We can have two types of monitor, which is the portable one, which we can carry it around and is used to troubleshoot problem in the facility or electric distribution system. And the other one is the more permanent install unit, which are used to monitoring a longer term system performance in a facility. It can also provide data or also be connected to alarm if the certain threshold is exceeded. Moving on, to calculate AC voltage, to take the measurement of AC voltage, it can be done with power quality monitor, provided that its input range capability match the voltage range expected to be measured. There are many instruments that are capable to a direct connection up to 600 volt RMS. However, in higher voltage, PTs are required. PTs we can use the IEEE standard C57.13 uses voltage transformer instead of potential transformer or PT. Moving on, PT itself can act as a low pass filter. The amplitude and the phase response coupled with a cable and the input impedance of the monitor can be significantly altered and have multiple resonant points. Figure 1 and Figure 2 shows the frequency response as ratio correction RCF vs the frequency for an example PT circuit. If the connection are made to a capacitor coupled voltage transformer, only the power frequency voltage signals for which they are tuned should be considered as accurate. In the next subtopic, we're going to discuss about the monitoring instrument. The first one is the event indicator. Event indicator are data generated by the electromagnetic phenomena should be displayed in a indicator light or illuminate bar graph, or also an audible alarm, or sometimes three of these is combined together. Event indicator is important because human react when a sound or a visual signal act as a medium to tell them that something wrong with the system. In the event of the threshold is exceeded, any threshold that is not meant to be, maybe comparing a steady state and the voltage is swell from the steady state value, the voltage swell, it will tell the person the number of occurrence or maybe the time that it happens. It also store the data for people to further investigate the event in detail. Next one is the oscilloscope. Oscilloscope can be used to provide a visual representation of voltage and current when supplied with appropriate probes. Some allow a direct calculation of peak, average, RMS, and other values. For example, a clamp on CT, which is a current transformer, we can use a clamp on CT. We can use a clamp on CT to take the measurement of a current waveform. Okay, the next important term is the floating the scope. Floating the scope is when the shield conductor of a single-ended oscilloscope input is normally electrically tied to the equipment grounding conductor on the cord and the plug of the oscilloscope. Preferred method is to avoid using ground loop is to use the instrument grade PT, which are the potential transformer, or the optically isolate voltage probe in the conjunction with the oscilloscope. Okay, lastly, we're going to talk the caution when using instrument, when picking or choosing an instrument, because there are compatibility between the two, because some instrument use power supply and that power supply can affect the reading that we have taken. So in choosing our instrument, we should refer the instrument manuals, and we need to ask ourselves this question, the following question, because this question can avoid us. Okay, the first question is, what is the level of isolation between the instrument power supply and the instrument measurement circuit, and does the instrument power supply generate noises that will affect the readings, or the power consumption of the instrument influence the measurement? Does the instrument power supply contain transient protective device that can affect the measurement made with the instrument? Does the instrument operate correctly during power system variation that induce power quality problems? Are power cable that are susceptible to EMI/RFI being used that can introduce false reading in the instrument? Furthermore, other issues are arising when powering the instrument with the source different from the measuring point, such as what is the quality of power supplied to the instrument, and does it affect the measured data? Have ground loops have been introduced into the measurement setup? Does the placement of the instrument require excessive long power cord, voltage, and or current lead that may degrade the accuracy of the measurement? Could the long power cord and leads be the subject in inadvertent disconnection? So this question is important to be asked before we use a certain equipment for measurement of voltage or current, because we need to make an accurate measurement so that we can know what the problem in the power system, whether it's voltage sag, whether it's voltage swell, whether there's a problem in harmonic distortion, something like that. So this measurement is very important so that the engineer, the technician can determine the problem and can come up with a solution to get a better or a perfect AC voltage waveform. Okay, worse than not getting the data one is expecting is a getting bad data that is thought to be good, because this type of data is overlooked and passed on to the algorithm, where it can contribute to a significant error. Causes of a bad data can typically stem from human configuration or connection error. However, it can also lead to hardware malfunction and errors in algorithm. Some common example is include in the figure below. For what we can see from the figure below, missing data, large gap of data is often noticed. However, a small gap in data can easily miss. Latched data, another often overlooked anomaly, is latch data. Most parameters should have some form of randomness. If consecutive values are giving you the same numbers out to a significant decimal value, it is most likely latch. This can be caused by a malfunction in the processing or a communication handling. This can also show up as a false positive for latching if a measured value is using a fraction of bits resolution from the analog to a digital converter. The next one is the abnormal range. This is when a trend goes outside the normal range of operation. The cause can typically be a misconfiguration in the potential transformer or in the current transformer multiplier. Extreme values is another thing that we get when we do a measurement. Sometimes the values goes outside the range that do not seem physically possible. This could be due to a glitch in the processor or the parameter algorithm not processing the data correctly. Leaving these type of values unchecked can significantly affect the accuracy of post-process statistical data.
Assalamualaikum and have a good day, everyone. Okay, we are now going to continue to the application techniques of the IEEE 1159. Okay, in IEEE 1159, the application is one of the most important steps followed, since in this section, the precaution and safety of equipment and people around is involved. Okay, there are several steps for monitoring technique we should follow. The first one is the first step we need to follow is monitoring location. The second one is equipment connection. The third one is measurement threshold. The fourth one is installation time frame. I'm going to explain about the safety a little bit into one by one aspect. Okay, the first one is OSHA requirement. OSHA requirement is about OSHA has publishes many rules and regulation regarding safe working condition around electrical system. So these regulations are often made a part of law and should be followed. And next, the NFPA requirements. The NFPA requirement provide requirement for the selection of PPE when working on or near energized electrical equipment, which includes the following. In NFPA requirement, we include these two aspect is included, which is performing an incident energy analysis for the specific equipment and tasks being performed, or using the hazard or risk categories table. Okay, next we go to the general safety consideration. In this aspect, prior to the commencement of the installation connection, the installer should be familiar with the site that is being monitored. So for the safety consideration, the installer should be certain of the source of the local circuit to be monitored and note the voltage, ampacity, upflash exposure level where available, and next higher circuit interruption device location. Okay, next aspect is live part. The live part, often panel covers are removed for connection of monitoring equipment and remain partially open or unlocked during the monitoring period. Okay, we're going to the number 6. The point number 6, equipment placement. The equipment placement is the monitor should be placed securely so there is no chance of instrument movement and connection becoming loose. The last one is grounding. The grounding, we should place in the grounding. All instruments are capable of developing internal faults. The instrument power supply should be properly grounded through a 3-wire cord. Next, we are going to the monitoring location consideration aspect. Okay, in monitoring location consideration aspect, we have grouped into 6 points, which are, the first one is objective, the second one is facility power quality survey, the third one is knowledge of electric circuit, the fourth one is PT and CT specification, and the fifth one is IEEE STD 5.9, and the last one is diagnosing equipment performance problem. So basically, in the monitoring location, we are some variable that need to be considered, which is the dynamic of the load. The varies depend on subject. The location of power quality monitor dependent on the objective of the subject of the survey, and the last one is the system impedance. Next, we are going to the equipment connection. In equipment connection, there are some points that we need to know. The first one is power measurement. The second one is electrical circuit connection, and the third one is connection lead. The fourth one is sensing inputs. Next is ground terminals, and instrument power and intensive monitoring, quality of voltage of sensing connection, current monitoring, and measurement threshold. Okay, now we are going to the second last part, which is measurement threshold. In measurement threshold, there are 5 parts, which is objective, preparation, car equipment susceptibility consideration, electrical environment, and current consideration. Okay, so what is measurement threshold? Measurement threshold is monitor measure data continuously. However, if all data was stored, the monitor would quickly run out of memory. So the measurement threshold or triggers provide a means for determining what is and what is not recorded. And some power quality measurement instruments subdivided the recorded data into groups called event. So the proper setting of the threshold that determine whether the data gathered are useful data to keep. Threshold set to low result in irrelevant data and threshold set to high result in insufficient data. So we go to the last part, which is installation time frame. In this installation time frame, we have four main parts, which is objective, baseline, power monitoring, problem solution monitoring, and power supply monitoring. So what is installation time frame? The installation time frame refers to the monitoring period or duration and time during which monitoring is occurring. As an example, time of year, day and week. Gathering data at the appropriate time and for the appropriate duration is necessary to properly diagnose power quality events. So the objective of the installation time frame is the direct function of the monitoring objective. Usually the monitoring period attempts to capture a complete power period and in an interval in which the power usage pattern begins to repeat itself. However, for a seasonal problem, the monitoring period might be for months.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nur Haslina binti Muhammad Razali. So I'm gonna proceed with the interpreting power monitor result. So interpreting power monitor result is the troubleshooting and solving power related problem involve a number of issues. So problems are solved by the following method. First one is careful evaluation of the loading and loads. Second, verification of correct wiring and grounding of the electrical system. Third, installing power monitoring equipment to obtain system data and characteristic. And fourth, involving the local power provider to understand if there were coincidental events on their system. Interpreting data summaries is one of the first steps in interpreting the data from a power monitor is to examine the power monitor configuration and confirm that it matches the power system monitored. An accurate summary of the data acquired typically required monitoring over some time interval. This is the step-by-step of the interpreting data summaries. The first step is measurement validation. This step's purpose is to assure that the data set is reasonable based on the circuit configuration, monitor capabilities, and monitor connection method. The second step is summary preparation. A data summary table is typically focused on power monitoring measurement. Their details and ordered chronologically to allow quick correlation with a power quality problem, for example, process misoperation. Okay, table below shows some possible column headings of a summary table. The third step is interpreting summaries. Once certain summarized data is valid, the first round of interpretation can take place. A chronological overview of what occurred during the monitoring interval can be reviewed. This histogram should be compared to load cycle, failure logs, equipment specification, result from personal interviews, or any other information collected. Critical data extraction is to help determine what data need to be examined more closely. This step will be used if the summaries do not provide an actual solution to a problem. Okay, this is step by step of critical data extraction. So the first step is determining critical event from multiple disturbance. Determining critical events involve collecting all disturbance that appear to describe the same event and then analyzing each disturbance as a part of the whole. Figure A to Figure B shows the result of an older monitor which generated three graphs relating to the same events. Notice in figure B that the wave-shape disturbance showing the restoration of power has a timestamp equal to the initial wave-shape disturbance time plus the interruption duration from the set graph. This type of correlation is very useful to identify critical event. Second step is event reality check. Reality check is an assurance that recorded data are reasonable based on the circuit configuration and monitoring connection method. Figure A, B, and C demonstrate the need for an event reality check. Interpreting critical event. Once the critical event have been determined and checked, the next step of interpretation begins. If the analysis of the summaries identified particular event, this should now be examined. If no specific event were identified, then each event should be inspected based on the chronological order. Keep in mind that an event can consist of more than one graph or report. Table 1 is a reference chart of data interpretation. For the condition given, it identifies the analysis technique to be used and locate that by subclause number. A decision of the characteristic and possible causes are included in each subclause. And lastly, verifying data interpretation. To double-check the solution or guess to see if it is indeed the right one for the problem. This check can be accomplished through examining the guidelines in D1 and D2 for post-monitoring. D1 post-monitoring for verification is the failing equipment now operation correctly. This is the question that should be asked when we do post monitoring for verification. And the second question is there a reduction or elimination of the disturbance in question? So for D2 is post monitoring for system interaction. Post monitoring help to determine whether any other concern have arisen because of the implementation of a solution. That's all from us. Thank you.